What is up, everybody? It is Jason Watts, and once again, I'm trying to get a bit more content out there for you. And in this series, it's a little bit more shorter topics, very important, but it's going to be things that I think are essential for all engineers and all control engineers to really understand in order to take their automation experience to the next level. Now, I'll be recording these from my home studio instead of my lab, and so you're probably not going to see as much as my face on them, and that might be sad for some of you, but maybe it'll make the channel grow. Either way, I hope you enjoy the content, and yeah, like, subscribe, and if you want to join in the conversation, be sure to join in the Discord. It's in the description below. So you've made it here in your journey because you have been turning on and off lights, maybe turning on and off some valves, opening and closing things, and now you're really wanting to move something, whether that be from a simple pump to maybe a conveyor belt, all the way up to maybe you're looking at doing some robotics and really want to dive into this stuff. But everything that all of this is based on are some sort of motor. Motors move the world, and we're going to go through the basics of AC motors in this video. Now, normally a lot of my content is very Siemens specific, and I do a lot of education on that sort of stuff. If that's something you're interested in, check out the rest of the channel. But this video has nothing to do with Siemens, and so it is vendor agnostic. Everything here, it doesn't matter if you're an Allen Bradley programmer, an Omron programmer, or even a Click PLC programmer from Automation Direct. This applies to you because this is about AC motors and VFDs. We're going to go through the basics to be able to start a conversation about how to use VFDs a little bit better. And we have to honestly start at the very beginning. We have to start at the motor. And what you have on the screen is very much probably the first motor you've experienced in your life, and you probably don't even remember it. At least if you're in the US or someplace to where you have a ceiling fan, when you were a baby or at some time, you woke up some point and saw what you have on the screen. You saw a weird looking shape that looks like some sort of bladed machine of death, and at some point somebody walked in and this thing started turning, and it would flip a switch and all of a sudden it would speed up and speed up and speed up until it got up to its speed and it ran that speed. And that's probably the first AC motor that you have ever seen in your life, and it is a very simple one. Yes, you could change the speed, but it's a single phase motor that honestly has a very simple operation. Now, we're not going to get into how the speeds would change on this motor, but we are going to talk about how you would change a speed on an industrial motor, because the same principles that apply to this ceiling fan apply to your industrial motor. Some of the two things that I want to start talking about at first is the fact that you have a fixed voltage and a fixed frequency of your line. So this ceiling fan, if you're in the US, it's going to be 120 volts and 60 hertz. If you're elsewhere in the world, this may be 230 volts and 50 hertz. But it's all single phase, and we would be looking at fixed voltages and fixed frequencies. Well, the same thing is, we have the same thing in our motors for industrial motors. And so let's go through and talk a little bit about how we go from this simple ceiling fan over to a much more complicated industrial motor, or at least it seems much more complicated, because this industrial motor has a lot different voltages. It's three-phase. It seems to be a lot different than this ceiling fan, but in practicality, it's not. One of the things that we have that we also need to talk about when we're talking about these motors is the fact that there's two pieces of every motor. There is the stator, which in this case is the stationary, stator, and then you have the rotor, so the thing that actually moves, rotor. And that is a horrible, that's not an E, that's an O, but you get the point. You have the stator, the stationary portion, and then you have the rotor, the part that moves. So in our ceiling fan example, it has a stator. It's the part that is the piece that's like attached up to the actual roof. And then you have the actual bladed part here that turns. So the stator would be the part that's fixed to the roof, and then the rotor would be the thing that moves. Same thing in an industrial motor. The thing about this industrial motor is the voltages, depending on where you are, can vary between 360 volts all the way up to 590 in some cases. And this is three-phase instead of single phase. The frequency will still be the same. In the US, it'll be 60 hertz. In other countries, it will probably be 50 hertz. And that honestly is the most important thing that we need to kind of correlate between these. The second thing that we're going to talk about is the torque that is available. And the torque, you just need to know that that is the available power. Even though power is something a little bit different, it's the ability to do work. So it's the force that is getting applied to the rotor. And we're not going to go too deep into it, but just know that we're going to be talking about torque, frequency, and rotor speed. The voltage is, in all of our things we're going to be talking about, is going to be a fixed voltage. And at first, we're going to be talking about a fixed frequency. Because just like in this fan, you have some sort of switch that you are going to throw. And when you go to start up this fan, you take this switch, you close it, and your voltage gets applied to the stator, and it starts to move the rotor. So there's a magnetic field in there that gets generated, and the rotor starts to turn and starts to speed up. But the voltage is already there. In our three-phase, it'll be, in the US, it'll be 480 volts. And then the rotor will start to slowly speed up. Depending on the situation, depending on how the motor is designed, it'll speed up at different rates, but it will speed up. This is called across the line, because we are taking our line voltage and applying it across our motor. So the line is instantly being applied across the stator and the windings of this motor. So across the line, you'll hear me talk about it like an across the line starter or something like that. And sometimes I'll say ATL. I'm from ATL, short for Atlanta, but that's not what I'm talking about. I'm talking about across the line. So let's go through and talk about what this applies. So we said that, let's do it this way. Let's go this. Okay, we're going to clear all this. We're going to go back. And what you will see in industrial motors is what is called a speed and torque curve for a motor. And this, you'll see for every motor, there's some sort TORQUE curve for this motor. And these things are at a fixed frequency and voltage. So these will be across the line, ATL. So remember, we are across the line. In the US, this would be 480 volts and 60 hertz. And so what would happen is, this motor torque curve will start at some torque. It will, as we start to speed up, the motor will be able to generate less torque, and then it will be able to generate more torque, and then it will drop off here and hit 60 hertz. So this crossover point right here, I kind of did that. at 60 hertz, when whatever, depending on the winding design of the motor, there will be a certain speed that when the magnetic field matches 60 hertz, which is the line frequency, it won't, in this particular design of motor, it will not be able to produce any torque, but it will be running at a certain speed. So our actual speed in the US for a 4-pole motor, and again, this is how the design of the motor, at 60 hertz, this would be 1800 RPM. Well, every motor, every system has a little bit of drag and is applying a little bit of torque. So again, this is the rotor speed, and this is the torque. Or it's also the current. The values, the actual numbers will be different, but torque and current are always directly proportional. So the more torque you have, the more current you will have. The more current you will have normally, the more torque you will have. As we see, the rotor speed, as it speeds up, the torque will change. And so we could see here that we can go at a certain rotor speed up to this torque curve and see that it will change. And so as the rotor is speeding up, because it is always trying to get to whatever the line frequency is, we can see that this will output some sort of torque and output some sort of current at a certain rotor speed. Well, the rated speed is going to be somewhere around here. It's going to go down. And for most 4-pole motors in the US, this is going to be about 1785 or so RPM. And then you will have, this will go over and there will be some sort of rated torque. And that will give you at 1785 RPM, at that torque, it will give you your power rating. So this is across the line. So this is only for 60 hertz. So if you put a 480 volt source at 60 hertz onto a 4-pole motor, this is showing how that motor will react. If you were running at half the speed, which would be around 900 RPM, then your motor is only going to be able to output so much torque. If your motor, the load requires more torque, it will slow down further and eventually stall. So this is what happens with an across the line starter is once you get it up to speed, you don't ever want to drop below this point here. You never want to slow it down. So this will kind of be the stall torque because it falls off this curve. So you're saying, okay, that's for across the line. That's pretty cool. Now, what happens if I want to change the speed? Because this only runs at one speed. So if you throw this across the line at 60 hertz, then it will try to run at around 1785 RPMs if you're in the US for a 4-pole motor. Well, what if I wanted to change the speed of this motor? Well, I would have to change the line frequency. And we kind of talked about that before. You can't really do that. So what we need to do is to put a different device in order to modify our line frequency. Whatever the motor sees, we need to modify this line frequency. And so what we will use is a variable frequency drive, a VFD. And that's probably why you're here. But you need to understand this basic concept that what we are doing is changing the frequency of the line of an across the line motor. So take from across the line, and how do we relate this torque curve that you may or may not have seen before? How do we relate this torque curve to our variable frequency drive? How do we change it? Because you say, okay, we're just going to change the speed and it's going to come down and we're going to do the same thing. Not exactly, because what we are doing is this motor that we have on this torque curve is always trying to run at 1785 RPM. What if we don't want to run it at 1785 RPM? What if we want to actually run it and produce good torque at 900 RPM? Well, that's where the VFD comes in. So let's go through and check that out now. This, delete everything. And let's go back and redraw this torque curve. And I'll draw one kind of at 60 hertz, what you would expect. We just saw this. Now, what a VFD does, because instead of changing the rotor speed, it is actually changing the line speed. What you end up with is the production of essentially lots and lots of curve. And so what you will have is lots and lots of curves that look like this. And so as you get slower and slower, it's like you're adding together all of the different torque curves at different speeds. So what I've drawn here, and I know it's a bit confusing, this first torque curve was at 60 hertz. The second curve was maybe at 58 hertz. This third one is at, looks like it's about maybe 55 hertz. And so on and so forth. As we go down, we notice that even when we get down here at, we'll say this is probably around 25 hertz, this last one. This last one is at 25 hertz. If you notice, we rated our original motor here at this point. So it had at 1785, it had the same amount of torque, which torque equals horsepower, right? So at a certain speed. Well, guess what? When you put a VFD on, you can find that point at every single curve. So now, instead of having this dip in our curve or dip in our torque up here, like we had across the line, if we slowed down to 25 or 30 hertz, we have exactly the rated torque. So the same amount of torque that this motor was rated for at 1785 RPM at 60 hertz, whatever torque we had available, we have that available here. So with a VFD, you get the rated torque, drew that backwards, but you get the rated torque at the rated all the way through the speed range. And it's because we are changing that frequency. Now, torque, the torque value does not directly equal our power. So our horsepower or kW, because horsepower and kW matters for speed. So your power, your overall power at this point is lower because you are traveling or you were spinning slower. So your speed is less, so your overall power is less. So how does a VFD do this? So a VFD has to do something in order to change the frequency. And what it does is a frequency converter. So it takes an AC source, it converts it into DC, then it converts it back into AC at whatever frequency it wants. So you have in every single drive system, well, I say that. There are some exceptions, but you're probably not going to use them, or at least not for a while. Every single drive system has some sort of rectifier, has some sort of DC bus, which has really big capacitors. That's why we draw it this way. And then we have some sort of inverter. And you may be familiar with some of these terms because rectifiers and inverters are everywhere. You have rectifiers are how you create a DC voltage. Inverters are you have sine wave inverters for your car. You have any sort of like photo cell, like renewable energy. You have inverters. Well, guess what? That's what VFDs are. At their core, they take AC, convert it into DC, and then take that DC voltage and convert it into an AC voltage with a variable frequency. And every vendor does this same thing. Every vendor has some sort of drive that's this technology, and this is the most common drive for AC. And that's kind of the point of where we need to go today, because you need to understand that the motors themselves are all the same, and if you put a standard voltage and at a fixed frequency onto an industrial motor, it is going to turn at its rated frequency. If you put a variable frequency device, variable frequency drive there and change the frequency, you will change the speed. You will not limit your torque though, which is pretty cool. So we're going to talk about in the next video about a little bit more of the actual VFD, some of the control schemes about this, but this is the basics that you need to know about a motor and how an AC motor and how it interacts with a variable frequency drive. Now, I will say that this content is available in a book that my dad and I have written called AC Motors and Drives, and is a part of a series, a fundamental series that if you are either coming from the plant floor where you have experience with keeping up machinery, then this book will fill in the gaps between this kind of motor theory and what you have been working with for years. Also, if you have a little bit of education with motors, maybe some electrical engineering classes, it will fill in the gap between that theory that you've seen and then some of the practical applications. The link for that book is in the description below, and it's something that you could pick up if you feel inclined to do that. We're going to continue this discussion in another video here, but if you've made it this far and this has been helpful, be sure to like and subscribe to the channel. We've got a lot of different things that we do. We do live streams, we do videos, and there's a community, a Discord community that's available for you as well. But in the meantime, hope you are looking forward to the next video in this series about AC motors and AC drives. I hope that it has been helpful and you have a good rest of your day.